Hey guys, welcome back. Day 41. We got calorimetry today. So we're going to talk about energy, talk about specific heat, and then obviously the change in temperature. So how is heat measured? All right. So how are we going to measure some heat? Well, calorimetry is what we do. Calorimeter. Okay. And so we measure temperature change, and then we calculate the heat change. All right. And so heat, the units for heat will be in joules. Right, and the symbol Q. Mass, we're going to use grams, and so it'll be M. Specific heat. What is specific heat? Well, we use C for that, and that is joules per gram degrees Celsius. All right, so specific heat is the quantity of heat required to raise the temperature of 1 gram of a substance, right? Usually a pure substance, by 1 degree, whether it's Kelvin or 1 degree Celsius or 1 Kelvin. All right. And then temperature change, technically speaking, it is in Kelvin, but it can also be in degrees Celsius because the change is the same. So that's delta T. And technically it's T final minus T initial, all right, because this is directional. All right, so the Q equals MC delta T. Now, mass times specific heat would end up being joules per degree Celsius, and that's heat. Oh, that's bad A. Sorry, heat capacity. So heat capacity is the quantity of heat required to raise the temperature of the system, the whole system, right? And so the intensive property of specific heat depends on how much you have. It's independent of how much you have, excuse me, I said that backwards. So the specific heat of water is 4.184 joules per gram degree Celsius, no matter how much water you have. The heat capacity is extensive, means it depends on what your system is, right? How big it is, how small it is, it's per system. All right. So now, when we talk about heat transfer, right, we know that when two substances of different temperature are combined, right, heat flows from it's hot to cold, and we know this. Some of us have learned it very painfully, but we know this. All right. Okay. And so the two heats, Q, one is the system, and one is the surroundings. And of course, one's negative. And we always make it positive for the system. So the heat transfer, heat lost by the oven is gained by 9 knuckles, right? If that happens, right? That's exactly what happens. So there's two types. There's bomb calorimetry and coffee cup calorimetry. Now, in bomb calorimetry, right? So for bomb, a bomb looks something like this, where you have some type of sealed container, right? And it's thick-walled, all right? And then down here, it has a sample. So it has some type of sample on there. I was trying to make a rectangular sample. That's your sample down there, okay? And then you have in here, right, this bomb this is inside a bomb, and it's sealed, right? Also is in there as O2, okay? And then all around this is H2O, and then you have a thermometer in here somehow. You get your thermometer, and that probably somehow sticks out, right, to read. And what happens is we burn this sample in here, right? And the heat goes out into the water, and we can measure the double temperature change of the water. But because of this, the way it works, it is no work's done, all right? Okay, since no work's done, delta E equals Q. Or delta U, actually. Our book goes delta U. Delta U equals Q. Or QV. Coffee cup is what we use, right? Because they're much cheaper. Now, we actually have styrofoam calorimeters. They got their lid, so it's got a lid on it, right? You have your thermometer, right, over here, and it's just thick styrofoam. And it happens open to air because the styrofoam is not sealed. And so that's what we have for calorimetry, all right? And so we use the coffee cup one, and that measures the heat of the reaction. So for example, let's do a couple examples with calorimetry. First one, how much heat is required to raise the temperature of 50 grams of water from 20 degrees Celsius to 45. And it gives you the specific heat of water is 4.184. So this is a Q equals MC delta T. Q is what we're looking for. M, mass. The mass of water is 50.0 grams. The specific heat of water is 4.184 joules per gram degrees Celsius. And delta T would be 45.0 degrees Celsius minus 20. Oh, wrong color. 20. Let's do it this way. All right. So Q, if we did that math, the 50 times the 4.184 times the 45 minus 20, right? I got 5,230 joules. All right? So that's how much heat's required to raise the temperature of 50 grams of water from 20 to 45. 5.23 kilojoules. Next up is how much will the temperature rise? So there's your question. All right. How much will the temperature rise if 1,000 joules of energy are used to heat a 10-gram block of copper? It gives you the specific heat of copper is 0.385. So again, this is also a Q equals MC delta T. Right? This is Q. This is M. That's C. And delta T is the question mark. All right? Now, sometimes if you want to do it, Q equals M equals C equals delta T equals. If that helps you out, feel free to do it this way. 0.385 joules per gram degrees Celsius, 10 grams, and 1,000 joules. So that means we have 4 sig figs on the joules. So if I plug in 1,000 joules equals 10 grams multiplied by 0.385 joules per gram degrees Celsius, and we want to know what delta T is. All right, and so it looks like if you divide, I get basically 259.7. So if I have 3 sig figs, so 260 degrees Celsius. So that's what we get there. So that's just Q equals MC delta T. That is when we are in one state of matter. So now if we look at changes of state. All right. There's solid to liquid, liquid to vapor. So solid to liquid, we call this melting or fusion. And vapor to liquid to vapor, we call that vaporization. Evaporation can happen, but that's only not at the boiling point. Boiling is at the boiling point. Vaporization is any phase change. All right? So now we know that changes of state take place at constant temperature. Think about it. Q equals mc delta T. If we're constant temperature, that's not changes. There's no change in delta T. That's 0. That means Q is 0. But you empirically know that that's not going to work for like boiling water. If you're boiling water at home, which we all probably have, right? You have the water on the burner. If you take the boiling water off the burner, it stops boiling. However, you got to have the heat keep on to make it keep boiling. So you're adding heat, but you're not changing the temperature. So something else is going on. And there's really two formulas because the distance here, this arrow in purple, solid to liquid, is different than that arrow from liquid to gas. Right? They have different sizes, different amount of energy required to go from a solid to a liquid than it is from a liquid to a gas. It's just different. It's not right or wrong. It's just there's a reason for it, and it's different. So the formula is still Q, amount of heat, right? And it's still Q for the amount of heat. All right? And then there's this new term, delta H, right? What is delta H? Delta H, right, is heat transfer at constant pressure, enthalpy. And so we have the enthalpy of fusion and the enthalpy of vaporization times the mass. All right, so we have the enthalpy or heat of fusion and the enthalpy or heat of vaporization. Okay. Now, why does that weigh? So when we go from solid to gas, right? Bonds are broken. That means energy is required. It's endothermic. Energy is positive. It needs to happen. Like to melt ice, you need to add energy to it. Now, sometimes that amount of energy is fine in the room, right? You bring it out of the freezer, and hopefully you take it outside, and it's not that cold, and it melts. But it can be below the freezing point of water outside, and the ice will stay ice. But you need to add heat to that solid water to get it to become a gas. And that's what happens. So now, if we look at this heating curve, all right, here's a heating curve, all right? And so there's 5 spots, all right? So I can start ice down here, and what do we have? We'll do, this is 0 degrees Celsius right here, and 100 degrees Celsius, which is there, all right? So far, so good. Does that kind of make sense? So that's your, right, boiling point of water and your melting point of water. We can start with ice below 0, can't we? We can start below 0. And the reason we can start below 0 is ice, obviously, in your freezer is below 0. It can get pretty cold. And so you can warm ice, believe it or not. You can warm ice, right? And so to warm ice, right, heat or warm ice, it's a Q equals mc delta T. But now the C of ice is different. That's different than the C of water, all right? The mass of the ice is the same. The mass of the ice, the mass of water, it's still the same amount. So M, all these M's are the same, okay? So, because we're doing what, 10 grams of ice? So all the M's, same M, same M, same M, same M, same M. You have 10 grams of H2O solid, right, going to H2O gas. Right? So 10 grams of H2O is 10 grams of H2O solid going to 10 grams of H2O gas. All right? 10 grams. All right? That's what's going on. Negative 10. All right? So this is delta T of ice. And this is the C of ice. Then you got delta HF times the mass. Then you have the specific heat of water here, right? And this is water. And then you'll have steam here and steam there, right? So they're different delta T's and they're different C's because it depends on what state it's in. All right? And so let's recap. 1, right? Heat, that's heat the ice, all right? Melt the ice. And so melting the ice is right there, right? We're not changing temperature, right? You guys see temperatures here. So that's temperature going up. And this is just heat added. So that's more and more heat added. What happens? It's kind of like time, but it's actually heat added. And so we start, warm up, and then it's going to melt. And then step 3, once it melts, here at step 3, we warm the water to its boiling point. All right? And then once we're at the boiling point, we will vaporize the water. And delta HV, which is right here, is 2260 joules per gram. Delta HF is 333 joules per gram. So it's a lot more energy to boil water or vaporize water than it is to melt it. Then step 5, here we're heating the steam. Right? So that's the heating curve for water. And you just add all those steps. If that makes sense. I would add all those steps. Right? And so if we look, the overall heat, Q, right? The mass of the ice is 10 grams. All right? The specific heat of ice, I got 2.1 joules per gram degrees Celsius. And we're going from negative 10 down here to 0, so 10 degrees Celsius. Plus melting the ice. We're going to melt the ice. I got 333 joules per gram. That's delta HF times our 10 grams. Plus, still 10 grams. But now the specific heat is 4.184 joules per gram degrees Celsius. And it's 100 degrees Celsius minus 0 degrees Celsius, right? 100 degrees Celsius. And I'm just going to do it this way for space. And then we got the steam, right? Delta HV is 2260 joules per gram. And we got 10 grams. And finally, we have 10 grams of steam. Specific heat of steam is 2.0. And we're going to 110, correct? 110, yes. So 10 degrees Celsius for that. All right, so we have step 1. This is warming the ice. Step 2, which is melting. Step 3, which is warming the water. Step 4, which is boiling. Step 5, warming steam. And it's an overall Q, right? Like all the energy is additive. Just like if you shop and you go to 4 stores, all the money you spend is additive. So it looks like in purple, it's 210 joules to warm the ice. It is 3,330 joules to melt the ice. It is 4,184 joules to warm the water. It is 22,600 joules to boil. And it looks like it's 200 joules to hit the steam, make the steam hot. And so if we add all those up, You know, the 210 plus the 3,330 plus the 4.184, 4,184 plus 22,600 plus 200. I get 30,524 joules, or 30.5 kilojoules. So that's a heating curve for water. You can have heating curves for ethanol and other ones as well, right? All right, so now it's time for examples. Let's do a couple examples. All right. I have 20.5 grams of ice. I add to 128 grams of water at 76.5. All right. So, ice at 0, water, that, right? What does this mean, this insulated container? So we are in chemistry land, so we're going to assume no heat gained or lost, right, from this situation, okay? No, that's it, okay? We are going to calculate the final temperature. Specific heat of water and heat of fusion of ice. Excellent. All right, so our two, I have ice and I have water. And they both have a heat and they equal each other, all right? So the heat from the ice and the heat from the water, right? So which one's gaining and which one's losing? Well, I think the ice is warming, so that means the ice is positive and the water is negative, right? Energy is going from the water to the ice, okay? So now, what is the ice physically doing? The ice side, it needs to melt, right? So if I had a picture of this thing, I have 76.5 degrees Celsius and 128 grams. And then we're going to put in a big old ice cube. That's 20.5 grams and 0 degrees Celsius. And we know energy is flowing from the water into the ice. That's what we know. All right, so that water is going to melt, right? Some of that ice is going to melt. Maybe all of it, we don't know. And then once it melts, remember melting is at 0 degrees Celsius, right? And then if it melts, also the melted has to warm the melted ice. All right, so it melts, and that's at 0 degrees Celsius. Warm melted ice from 0 degrees Celsius. And that's going to equal the water, which is going to start cooling, which is what we want. We want water to cool, right? That's why we add ice to our drinks, if you guys are like that. Formulas. Melting ice. Delta H F times the mass of ice plus the mass of ice. Your specific heat now, what's your specific heat? Your specific heat, since it's now melted, it's no longer the specific heat of ice. Even though it was ice, it's no longer ice. Okay, so it was ice when we started at 0. It melts, it becomes liquid, so that means we need the specific heat of water. And then we need delta T of ice. And that's going to equal negative the mass of the water, specific heat of water, and delta T of the water. All right? So now I have my equation set up. What's physically going on? All right, I'm going to expand this one more time. So delta HF times the mass of ice plus the mass of the ice, our specific heat of water. T final is what we're looking for, minus the initial temperature for the ice, equals negative mass of the water, specific heat of water, the final temperature, because the final temperature is the same for both, minus the initial temperature of the water. Wow. All right, so now all these variables have a number from the problem we're going to dive in. Delta H, F, heat fusion, 333 joules per gram. 10 grams, right? No, 20.5 grams, excuse me, 20.5 grams plus 20.5 grams. Specific heat, now it's liquid water, 4.184 joules per gram degrees Celsius. The final temperature minus the initial temperature was 0. How nice. It's ice. So that's the left side. The right side, mass of the water, I think that's 128 grams. 4.184 is the specific heat of water. Joules per gram, degrees Celsius. And then TF, it's the same for both, right? The final temperature is the same for both. Minus the initial temperature of 76.5. Whew. Now with that, hopefully that's very comforting if we get to this point. Because the chemistry is done, we just got to do some algebra. All right? So the first, I get right here, 33 times 20.5, I get 6826.5 joules. And we're going to put the units in a different color. Now here, right, because this, I can just make that nothing, right? I can cancel that out. So now I just do 20.5 times 4.14 times TF, and it's good. So if I do that, I get 85.8 and the units would be what? The grams are gone. It's joules per degree Celsius, right? Equals. Now, in this one, I have to do the negative times 128 times 4.14 times TF and the negative times 128 times 4.14 times the negative 76.5. So you have to distribute that. So I would do the 128 times the 4.14 and then distribute that. And so it looks like I get negative 536 maybe. And that would be joules. Oh, I put my TF here. I even left the space. I'm sorry, guys. You're probably asking, what happened to TF? It was supposed to be there. All right, maybe I got excited. I don't know. Joules per degree Celsius times TF. Then it's going to be positive 40,970 joules. Hopefully, we're getting around these numbers. All right, what do we have to do? We're going to have to add 536 joules per degree Celsius TF both sides, which means I'm going to take this number right here, the 6,826.5, and bring it over that way. All right? And so if we add the 5,306 to both sides, I get, what is that, 621.8 or 622? And that's joules per degree Celsius times TF equals, do the other math, I get 34,144 joules. And then I can just divide by 622 joules per degree Celsius. Degree Celsius comes up top. And my final temperature, I get 54.9 degrees Celsius. Wow. Right? And so if we look at this all together, right? I want this. I got my ice and my water. And that's the two systems. Even though they're the same substance, they're different temperatures, so we can treat them as different systems. The water's energy is going into the ice. All right? So the ice some of the ice is going to melt, and then it's going to warm. And then the water's going to cool down some. That's why we use the ice. And so melting ice, delta H times the mass, then So you're either changing temperature, which is this one, or you're changing state, which is the first one. So we're changing state, then we're warming up, changing temperature. And this one's just changing temperature, it's cooling down for the water. So then we plug in, remember it's T final minus T initial. Now, there are other ways to do this on the right-hand side. You could make this positive, but then you have to flip those. And so it's just easier to make them negative if we know where the heat's going, because that's kind of what I want you to know anyway, right? I want you to know where the heat's coming from and going to. That's important. But then we just do the algebra, and we get 54.9 degrees Celsius. All right, one more. And I stole this one from when I was a grad student at Michigan State. I don't know which instructor wrote it. Dr. Hunter, Dr. Pollack, doesn't matter. I like a lot of their problems. They were fantastic. And so this is one of them, and I thought it was a great problem. And so here it is. You got 20 grams of steam at 100 is bubbled into a mixture of 50 grams of water, 20 grams of ice, where all the steam condenses to water. The question is, what is the composition of the steam or the system at the end? Not the steam, the system. And so there's going to be an amount of ice that we need to calculate and an amount of liquid water that we have to calculate. All right? So kind of what's going on here is that you would have some type of system. All right? No, it didn't snap to a square. That did. And then you have in here some type of way to get steam in. So you got steam coming in, and in this I have, what is it, 50 grams of water, right? And I have a lot more ice, right? 200 grams of ice. So big ice cube. So what's going on? So I got 50 grams of steam coming in. All right, so since we got 50 grams of steam coming in, what's going to happen? So some of the ice is going to melt. Now, my question to you in this one, let's think about this. Should I set it up like the last one? Well, there's a lot there, right? There's a lot there. Do we need to know the final temperature? I don't think so. All right? I don't think so. It doesn't ask for the final temperature. It asks for how many grams of ice and how many grams of water. So the question is, does all the ice melt? That's a good question. Because if all the ice melts, right, then I would just add everything to the water column and that would be it. So the question is, how much energy do we have to melt the ice? That makes sense? How much energy do we have to melt the ice? Well, which giving off energy? The source of energy is the steam. Right? That's the source of energy. And the steam is a gas, right? It can condense to a liquid, and then it can cool all the way down to 0. Right? 0 degrees Celsius. So I can condense and cool it all the way down to 0. So if all the ice does not melt in chemistry land here, the final temperature will be 0. Okay? So let's see. And since we have a lot less, we have, right, 10 times more ice than we do steam. Let's see how much of this ice stays. Maybe, right? So the steam, condensing for the steam, Q, from the steam, would be equal to delta HV, heat of vaporization, times the mass of steam, and the mass C delta T. The mass of the steam, specific heat now of liquid water because it condensed, right? It's now liquid, and delta T of that steam. All right, so I'm just going to write Q equals delta HV is 2260 joules per gram. And our steam was 20 grams, right? Yeah, 20.0 grams plus 20 grams. Oh, not plus, sorry. Let's go with 4.184 joules per gram degrees Celsius. And then I'm just going to go to 100 degrees Celsius here. I want this all positive. It's heat being released, right? So it's either all negative or all positive. I'm just going to do absolute value, make it positive, right? How much money do we have to spend? Basically is what I'm asking. So if we do this, heat from the steam, right? The most I can get is 53,568 joules. And this is the energy available from steam to melt the ice. Okay, that's how much I can do it. Right? That's going all the way down to 0 degrees Celsius. So now, let's look at the ice part of you. If we look at the ice, that would just melt, right? It just melts. That's it. We don't care about anything else. If it melts, that's good. It's not going to boil, all right? So it doesn't melt. Q for the ice equal delta H times the mass, right? So delta HF times the mass of ice. Well, I know what Q is. Q is going to be 53,568 joules. That's what we have. Delta H is 333 joules per gram. And mass of ice. So mass of ice, does that equal more than 200 or less than 200 or exactly 200? So if we take the 53,568, divide it by 3333, I think I get 161 grams of ice melts. So that's how much melts. All right. So if that's how much melts, what did we start with? So let's look at everything. The start of this process, we had 20 grams of steam. We had 50 grams of water. And 200 grams of ice. All of the steam comes over. And we're subtracting 161 grams and adding 161 grams from the ice. All right. So that means in the water category, I got the 50 plus the 20 is 70 plus the 161. I got 231 grams of water, liquid water. And then 200 minus the 161, looks like it's 39 grams of ice remaining. Right, so that's the composition of the system at the end. So if I slowly scroll back up, it's 39 grams of ice and 231 grams of liquid water. Whew! So let's recap that. We had steam being bubbled into, right? The steam's being bubbled into this ice-water mixture. And what happens? The steam disappears, becomes liquid water. What happens to the ice? How much does it melt? Well, we found the maximum energy that we can do it from the steam, right? It can melt and then it can cool down to 0. Right? That's what it can do. Then we figure that out with the algebra here, and we got that's how much energy can be released. We took the energy that can be released in ice melting here, Q, and that's how much energy it takes per gram to melt ice. And so we found the mass. We did that out. We found that this much melts. All right. And so then we figured out how much is left. All right. So those two problems. I love those two types of problems. They're always, I always pick them for tests and exams. But, and those are the hard ones. So hopefully, if you have any questions, reach out to me. All right. Don't hesitate. Otherwise, that'll be it. We'll see you guys in the next video. Take care.